Me.
So I,
That's good.
Yeah, I think, like, can you just check the audio?
Okay, well, Sasha, I'm gonna. Is this thing muted now?
yeah,
It's off. I mean, my voice is actually that loud. Yeah. Look at that. Okay. Well, hi everyone. All right. I'm so thankful for you for coming. I'm excited to share with you this work that I've been doing. So this is all work that has come from my research group at Clemson. Um, this is mainly an astronomy talk, but I've done my best to include things for people that I know have backgrounds in math, non-astrophysics, physics, uh, philosophy. There's nothing formal, but maybe some food for thought related specifically to the use of artificial intelligence. Um, it occurred to me after I sent that really long talk title, predicting the electromagnetic and gravitational wave signatures of binary black holes using AI coding agents. I should just have called it this. But this would have been too mysterious. But it would be accurate. The talk is appropriately about black holes, specifically the study of binary black holes using gravitational waves. And the AI part of it is going to be very practical. I'm just going to talk about some questions that arise in the quality, reproducibility, and maintainability of astrophysics software codes, and how that might be improved on through the use of artificial intelligence. All right, so yeah, there's my outline. So something for astronomers. Physics. I'm going to make sure there's some nice basic physics, just classical mechanics type stuff, and hydrodynamics. All right, so most of the talk will kind of be in this little uh, range right there. Okay, and then for the math and philosophers, good luck to everybody. Okay, so it feels a little silly to introduce a black hole with the Black Hole Initiative. There are two basic kinds. Okay, we have stellar mass black holes. These objects are discovered through their X-ray emission when exist as members of binary systems. They can accrete gas from a donor star, and they form this luminous accretion disk. So that's the name of this illustrated feature around the stellar mass black hole. So these are mostly galactic objects. On the other end of the mass spectrum, we have supermassive black holes. One is a Hubble image of one is here. In this image that is referred to as an active galactic nucleus. The acronym for that is AGN. And here the AGN is producing these powerful jets of plasma that are emanating into space. And the energy supply for all this stuff is a central supermassive black hole. As far as we know, every galaxy in the universe could host one of these things, including our own galaxy. And our own galaxy, the name of that object is Sagittarius A star. The mass range for these things, stellar mass black holes typically tens of times the mass of the sun, and supermassive black holes typically millions all the way up to billions of times the mass of the sun. In between these two, there is a hypothetical category of intermediate mass black holes, which we would say goes from maybe hundreds of times the mass of the sun up to perhaps 10 to the 5. And there's scarce electromagnetic evidence of these objects. They don't accrete. They likely don't exist in sufficiently gas-rich environments to produce very luminous electromagnetic signatures. There is some indirect evidence for them, but a theme of the talk will be that using gravitational waves, these things may be probed in the not too distant future. Okay, so historically, those black holes are studied electromagnetically. They produce light when gas falls into orbit around the black hole. Especially if it accretes through what we would refer to as a radiatively efficient accretion disk, that means that the gravitational energy of gas particles that are falling into the black hole, that gravitational energy is released almost completely in the form of photons, okay, making the objects extremely luminous, like in fact, like incredibly efficient generators of electromagnetic radiation. So when black holes exist in regions of space where there is a lot of gas, they can be incredibly luminous. in spite of being black holes. The other way that they can be studied, especially the massive ones, is by examining the trajectories of stars that are in orbit around black holes. That we would still refer to that as a mode of electromagnetic study. Gravitational waves are the next frontier, okay, and that study has been successful and ongoing since the first detections made by gravitational wave interferometers in 2015. So since then, there are detectors on the surface of the Earth, mainly in the LIGO and Virgo network, that measure the gravitational waves from binary stellar mass black holes when they're in the act of merging. Okay. We could refer to that as high frequency gravitational wave astronomy because those detectors are sensitive to gravitational waves that have frequencies in the range of like 100 to 1,000 hertz. All right. That high frequency corresponds to gravitational wave sources that are lighter, essentially stellar mass black holes. They're lighter, faster, and they orbit at that high frequency around the time that they're merging. So the next frontier in gravitational wave astronomy will be the low frequency end of the spectrum, heavier objects that orbit slower and which produce lower frequency gravitational waves as they spiral and merge. And that's going to be the focus of this talk. This is mainly where my group's work is focused, is in the lower frequency. All right, so this is just a quick sketch of the three basic categories of gravitational wave detectors. So here we have an image of the LIGO detector in Washington State. The detector arms are 4 kilometers. And again, the sensitivity range is like hundreds of hertz, corresponding to stellar mass compact object binaries. So that means this detector also measures the inspiral and merger of neutron-star binaries and neutron-star black hole binaries in addition to black hole binaries. In the middle here is a future detector, which is called LISA. Okay, that is Laser Interferometer Space Antenna. And it will be sensitive in the millihertz range. It will be a fleet of 3 satellites in orbit around the sun. And there will be 3 lasers, okay? 3 choose 2. At the lowest frequency end, there is this gravitational wave detection strategy that's referred to as a pulsar timing array. And I will say a little bit more about that in another few slides. The objects of interest for pulsar timing arrays are supermassive black hole binary systems that have relatively longer orbital periods than the sources for LISA. Okay, just a little bit of motivation. I like this picture. This is obviously from a simulation. This is done using the gadget code, not by my group. But this is like trillions of particles, okay, that were calculated using the gadget code, and this is just gravity. And essentially, this is what cosmic structure is expected to look like, what the universe looks like at a very large scale. And as structure grows hierarchically, I think you can see in this image here, galaxy clusters are created and galaxies, and these things fall together under their own gravity and they merge. And to the extent that black holes do likely exist in every galaxy, and galaxies merge, like this nice image here taken by Hubble, each of these things has a black hole in it. Those black holes are ultimately paired up. Okay, and when they do, they become gravitational wave sources. So when you see major galaxy mergers in pretty pictures like that, what I think is, okay, that's an incipient gravitational wave source. In about 1 billion years or so, this galaxy merger will complete through the process of mass segregation, or also you can identify this from dynamical friction. The black holes will sink to the center of the galaxy merger remnant. And when they do ultimately come into one another's gravitational sphere of influence, they'll go into orbit around one another. Okay, and at that time, they'll become gravitational wave sources.
Are those lines that we saw on the previous slide, are those the faraway look at numerous individual unions of supermassive black holes? Or are they somehow the net of all the great waves and producing those more cosmic ones?
Yeah, good. So I think that in this you're talking about this stuff, right?
Well, all the ones in this image.
Okay, yeah, the thing you can they're filaments of dark matter. So they're structures of dark matter, but these are at the scale of galaxy clusters or even superclusters. So I think one of these thingies here is probably representative of perhaps 100 galaxies. All right. And when those clusters of galaxies form, then the individual galaxy members of that cluster will ultimately merge with each other. And when they do, the supermassive black holes hosted in those galaxies will ultimately form bound pairs, which will be gravitational wave sources. The reason I find this image kind of compelling, it's like a powerful image, is that this, to the extent that low frequency gravitational wave sources will be produced in these filaments, you can think of the observation of those gravitational waves as a probe of this cosmic structure. Okay, yeah.
What's the redshift?
Good question. I didn't take note of it. Does anybody have a guess? What do you think? What at what redshift does the? I mean, it might be. It's scale free, right?
Scale.
I mean, in a sense, it is scale free, right? So I think if you were to just scale this, because it's just dark matter, it's dark matter only, and so the structures are hierarchical. So I think if I wanted to say, oh, these are galaxy clusters, I would say the redshift here has to be less than 3 or so. But if anybody else has a better guess, I'm open to it. The bar is covering up the reference there. So let me see if I can, there we go. So it was a Nature paper from 2020, first author Wong. So where should I put this thing?
You can hide, if you click the 3 dots at the end,
Yeah.
there's like hide floating controls.
Oh, good point. Okay. Hide.
Yeah.
Oh, thank you. Okay. Will you get messages from the audience in case somebody will?
Examining Zoom or messages.
Okay, thanks. Okay. Okay. Lost my clicker. Okay. Okay, this is a grid of JWST images of what we call dual AGNs. So these are major galaxy mergers that are in a more advanced stage. And they were picked out by James Webb observations because of the double luminous cores. Okay, so these are very likely objects in which the supermassive black holes in each of the merging galaxies both are actively accreting, okay, and are creating this double luminous core thing. So the projected separation in each of these images is, I think, so this one is 11 kiloparsecs. So that is like, 30,000 light years or something. It's still galaxy scale like. The smallest projected separations of any of these images, I think, is about 2 kiloparsecs. Below that, JWST is going to have a very hard time distinguishing 2 separate luminous cores from one another. But these dual AGNs are sort of further direct evidence that merging galaxies bring their black holes together. Okay, and so you can think of these as being like even more imminently gravitational wave sources. So the black holes in each of those luminous cores, they're not yet on a bound orbit around each other. Okay, so they're not yet even low frequency gravitational wave sources, but within 100 million years or so of these objects looking like that, those black holes will have sunk to the center of the rim and probably found each other and be orbiting. Okay, all right, so I just want to say a couple things about the basic physics of gravitational wave radiation. So I think it's instructive to see it as an analogy with electromagnetic dipole radiation. So this is the formula from textbook electromagnetism. that the radiated power by a rotating electric dipole is proportional to the square of the second time derivative of the dipole moment. Now, in principle, there would be an analogous thing for gravitational waves, except that because of Newton's third law, conservation of momentum, there is no time variation of the mass dipole moment of a distribution of mass. So there is no gravitational wave radiation associated with mass dipoles. They don't vary in time because of Newton's third law. So we go to the quadrupole order to see the radiation. And so this is the formula for the power radiated by a rotating mass quadrupole. Okay, and as you can see, it's proportional to the square of the third time derivative. All right, so this leads to a really interesting and simple demonstration of what binaries do as a result of gravitational wave radiation. Clearly, an orbiting binary system that is the textbook mass quadrupole. It's a dumbbell and it rotates, so it has a third time derivative, and so it does produce gravitational waves. Gravitational waves do carry energy, and they do carry angular momentum away from the system. Okay. If an orbiting binary system loses energy and angular momentum, it shrinks. So you can ask yourself, okay, now that the orbit has shrunk a little bit, does the gravitational wave power go up or down? Okay, hypothetically, if the gravitational wave power went down when the thing shrunk, there would just be vanishing gravitational wave power, right? And there would really not be anything too interesting. Okay, but it's easy to see that the opposite happens. Gravitational wave power goes up as the system shrinks. This third time derivative of the mass quadrupole moment is like the cube of the orbital frequency, capital omega. The mass quadrupole moment is proportional to the second power of the semi-major axis. That's the separation between the two components in the binary. Kepler's third law tells us that the orbital frequency is proportional to -3/2 power of the separation. And so if you just combine these things, you find the gravitational wave power rapidly increases as the orbit shrinks. So this means that orbital decay is a kind of an instability. Okay, so binaries are essentially unstable objects with respect to gravitational wave radiation. Okay, in practice, the time scale for this instability is interminable for well-separated or relatively low mass objects. So like the Earth around the sun, I think the Earth would spiral into the sun under gravitational wave radiation in some 10 trillion years or something. It's quite long. But for compact object binaries, that is black holes or neutron stars, white dwarfs, they can be close enough together that the gravitational wave in spiral time can be shorter than a Hubble time. Okay, and gravitational wave driven in spirals and ultimately mergers are expected to take place. Good. Okay. A couple notes about propagation. So gravitational waves are transverse waves, and they do this type of thing to objects. Okay, this is a cartoon of a gravitational wave interferometer. Essentially, these things count the number of wave periods between a pair of mirrors. Okay, and so they work by examining constructive or destructive interference of a combined beam in order to detect really minuscule changes in the length in the amount of distance between the mirrors. I'm going to come back now to pulsar timing arrays. So all I said so far about them is that they're a strategy for measuring very low frequency gravitational waves. What they actually are a catalog of pulsars in the galaxy. Okay, pulsars are neutron stars that rotate rapidly and with a very stable period. And that allows them to be exploited as clocks. So you can imagine looking in two directions in space, one perhaps over there, one over there, or in the back. I have a clock in the back of the room there. So I watch that clock and then I watch another clock over there. And I watch the rate at which the second hand goes, and I see that the second hand is ticking at a slightly higher rate and then at a slightly lower rate in an oscillatory fashion. And I see that the clock over there is doing the same thing, but they're out of phase by 90 degrees. That would be the signature of a gravitational wave. And so we can exploit an ensemble of pulsars in the galaxy to essentially play that game. They're all watched. Their rotation periods are very closely monitored over decades. And slight variations in the rate at which the pulses arrive to us at Earth indicate the presence of a gravitational wave that's propagating perpendicular to the line of sight, to the pulsar. So that's what's indicated here. Some test masses that are placed in two directions perpendicular to the wave propagation vector would do this. And the cases are for what's referred to as the plus versus the cross polarization of the gravitational wave. For the plus polarization, the test masses oscillate along the direction that they're arranged, and in the cross polarization, they oscillate in perpendicular direction. Okay, good. Any questions about how these pulsar timing arrays work? It's a pretty neat concept. I'll just say that they do now have a signal. All right, so as of 2 summers ago, there are 4 or 5 worldwide collaborations that are pulsar timing arrays. They all say they see evidence of a stochastic gravitational wave background. Okay, at a frequency somewhere in the range of 1 to 100 nanohertz. So yeah, that's like week-like up to year-like wave periods. The stochastic gravitational wave background signal that is identified by these pulsar timing arrays is consistent with being sourced by a population of supermassive black hole binaries in the universe. That doesn't mean it is definitely produced by such binaries, but it's largely consistent with one, except for being suspiciously strong. Right? So there's a little bit of concern about the signal measured by the PTAs that the amplitude of the gravitational wave background is just a little bit stronger than it should be, given the amount of mass we believe to be in black holes in the present day universe. So it's potentially interesting contention there. Okay, it's gonna go. Oh no. Okay. Okay, so aside from this indirect evidence from the pulsar timing arrays that the supermassive black hole binaries are out there, we have more indirect evidence electromagnetically. Okay, so this is a special case here. This is a 5 gigahertz radio image of an active galactic nucleus that is at 200 megaparsecs from the Earth. Right, so it's an active galaxy, but it has 2 distinct radio cores. And the object is called 402 plus 379. It's been studied since 2003 as a candidate supermassive black hole binary system. If it really is binary, the orbital period is estimated to be about 30,000 years. Okay, so that means that its gravitational waves are extremely weak, and the frequency is too low even to be detected by pulsar timing arrays. Okay, we would need to wait another 100 million years or so for this system to for its orbit to decay and the gravitational waves to become high frequency enough to be detected by a pulsar timing array. Okay, other ways we can detect these things indirectly is by examining the brightness of an active galaxy over many decades and looking for possible periodic variations in the brightness. You can imagine, like, what would cause a galaxy's light to get brighter and dimmer again with sinusoidal type regularity? What could do that other than an orbiting object? Some may say accretion physics. That may be, and they can masquerade. That's why I put can of worms here. It's very possible that sinusoidal type periodicity can essentially be faked as a side effect of stochastic variability, which is exhibited by all active galactic nuclei. So these sort of periodicity searches, they can produce very compelling candidates, but I don't think they can be used really as smoking guns. And I just put up here two very serious candidates. There are each of which are pretty deeply studied. This is PG 1302. It's exhibited some 5 wave periods now, and it seems to have about a 3-year orbital period. And this is OJ287. OJ287 is a blazar. Yeah, so it is an active galactic nucleus which is producing a relativistic jet, which is aligned with the line of sight to the Earth. And OJ287 is apparently special because it produces these 12-year periodic optical outbursts. The pulse structures even seem to be consistent, like each 12 years, the pulse produced, the outburst from OJ287 seems to have a double peaked structure. So it has been studied very deeply within a paradigm like this, in which a secondary black hole is in orbit around a larger primary black hole, and that there's an accretion disk around the primary black hole, which is being punctured by the secondary, and that the double peaked structure is associated with the passage of that secondary black hole in an inclined orbit through the accretion disk of the primary. All right, this is a very inviting picture. Turns out there are problems with it. I'm not going to go into that, but if any astronomy people really want to, I'm glad to later in the, but yes, question.
So you showed a zoo of JWST images before with fine or closely staged black holes. You said those in 100 million years would be VW sources. And then the pulsar timing array shows its back threshold. Is there a concordance between them? Do they meet somewhere so that ones you expect to evolve into GW sources have the sufficient number of them? There's a sufficient number of them that they match the PTA number?
Yeah, that's an excellent question. So I alluded to some kind of contention, and it is that when you try to play that game, it looks like there are not quite enough binaries to account for the amplitude of the signal that's being reported. Yeah, but you can play that game, yes, because you essentially from observing galaxies, you can estimate reasonably well the rate at which galaxies in the universe are merging. So if you further stipulate the mass of the black holes that are living there, you can say reasonably accurately what the time integrated gravitational wave power is from that population of black holes, whose number you're inferring from images such as the JWST dual AGNs. Okay, and the numbers,
You're saying they don't match?
they don't quite match. Yeah, the people say the discrepancy is as large as a factor of 10, that you need like 10 times more black holes to account for the gravitational wave amplitude that's being reported. Yeah.
So what's, okay, well,
Yeah, no, I attended a whole workshop on this a year ago, and it's not settled. Most people anticipate that the PTA signal will come down a bit, but other people point out that you can't really raise the number of black hole binaries in the universe because it's actually limited by the amount of black hole mass, the cosmic black hole mass. It's an elegant argument. I think, wow, yeah. This guy had his hand up first, I think.
No, I just want to know what's the meaning of a can of worms.
A can of worms was that the periodicity searches are questioned. And there are hundreds of candidate binaries, like AGNs that show apparently periodic variability. Okay. But apparently periodic is the can of worms. It's very hard to rule out other stochastic variability as the reason for the periodicity, the apparent periodicity. And even if you observe so many wave periods that you can be sure that the source is truly exhibiting sinusoidal type periodicity, it still doesn't uniquely implicate the presence of a binary black hole. Could be some other thing that oscillates periodically. Yeah.
That was a follow-up question. So the recent possible discovery of higher mass black holes at high redshift, could that alleviate a little bit this discrepancy between the expected and the measured?
not to the extent that we know the amount of black hole mass in the universe. Because if you took every black hole in the universe and assumed that it was built up through binary mergers, you would get a maximum integrated gravitational wave amplitude. Yeah, so the constraint comes uniquely from the amount of black hole mass in the present day universe. So if we've severely underestimated that, it would be a resolution to this. So, okay, I think that I have to move a bit faster. I'll maybe selectively omit some of the content on the upcoming slides. What I really want to show you is what happens when binaries interact with gas. Okay, that is the focus of my group's research. Okay, so it's the thing I'm going to talk to you most confidently about. So the reason that we need to understand the interaction between binaries and gas is mainly because of the electromagnetic signatures. Right? So just as individual black holes can be studied electromagnetically through the light that's emitted from their accretion disks, binary black holes, well, at least their electromagnetic signatures ought to be connected to the physics of binary disk interaction. Okay, and this is what I mean by binary disk interaction. So this is a movie of a simulation carried out with my group's hydrodynamics code. We call that thing Sailfish. And in this movie, these two black holes are surrounded by a disk of gas. Okay, so some terminology here. We call this thing a circumbinary accretion disk. Gas which falls from the circumbinary disk into orbit around the individual black holes forms these things that we call mini disks. Okay, the mini disks then go on to drain their gas into the respective black holes that they're forming around. Gas in the circumbinary disk, for the most part, it doesn't really know it's orbiting a binary. Far away here, you have just it just thinks there's some kind of central object there. Okay, but the quadrupole term in the gravitational potential increases rapidly as you get closer. So what happens is the gas that's orbiting within about 2 times the separation of the binary starts to feel a very strongly varying tidal field. Okay, and that gas gets pulled off of its otherwise circular orbits, or nearly circular orbits, in the disk. Okay, and that's what's happening here. This gas is being peeled from the inner edge of the circumbinary disk along these things that we call streamers. And those streamers then go on to collide with the mini disk. Okay, and those collisions lead to the dissipation of the gas orbital energy and the capture of the gas in single black hole orbits in the mini disks. Okay, so that's just
Actually, John,
yeah, go ahead.
are
Yeah.
those two black holes actually on a circular orbit?
And here they are on a circular orbit.
right?
They are,
Because
but you
light seems to see all sorts of non-circular motion. But
which is truly there. It's not, your eyes are not fooling you.
it's all in the gas.
There's only gas eccentricity here, but there's much of it.
Lot of it, yeah.
There's much of it. And I'll talk a bit about eccentric binary orbits, but in this case, the binary orbit is circular.
Circular, okay.
The circumbinary disk is truly eccentric. We understand the reason for that. The mini disks are also eccentric. We understand the reason for that. Okay, all right. So in the next, I'm going to show you a movie like that again. This time, actually, the orbit is eccentric, but that's just for fun. The argument I'm going to make is not contingent on the orbit being eccentric. It's just to show you that we can also simulate eccentric orbits. But the thing that I want to convey to you here is that, kind of surprisingly, the presence of a gas disk around a binary turns out to be capable of leading to orbital decay or expansion. This is rather surprising because if you try to invoke your physics intuition, that might come from the effect of dynamical friction. Okay, that's where an object like moving through a field of stars experiences a drag force. If you try to invoke that kind of intuition, you will conclude that a binary surrounded by a disk of gas experiences a sort of friction force and gives its angular momentum to the surrounding gas and then experiences orbital decay and it shrinks. But that can happen, but so can the opposite effect. And so the reason for that is that the gas which is orbiting at the edge of the inner edge of the circumbinary disk, it has a higher specific angular momentum than the binary. The binary has less specific angular momentum than the gas orbiting at the inner edge of the disk. Okay, so any gas parcels which are to be captured onto either of those black holes can actually deliver angular momentum to the binary. Okay, they can deliver more angular momentum than is needed to compensate the contracting effect of mass being added to the binary. So you can actually put a disk of gas around a binary and cause the binary to expand. Yeah.
What happens to these black holes?
Okay, so in this simulation, it doesn't matter. It doesn't matter because the physics is so incredibly simple as to be scale-free.
But does how quickly the deliver the angle parts depend on the accretion rate?
It does, but the sign does not depend on the accretion rate. So the rate at which you move the separation larger or smaller doesn't depend on the quantity of gas. Yeah, these are also done in the simulations are done in a test fluid limit. Okay, so the forces from the black holes act on the gas, but the gas does not feed back to evolve the orbit of the binary in this simulation. Okay, so we now understand that the tendency for gas to widen or contract a binary, it can be understood from a very simple ratio of accretion rates. It is simply the rate at which mass, it's the ratio of the rates at which mass falls from the circumbinary disk onto a black hole, we call that m dot accreted, to the rate at which gas escapes. And as you can see in the movie that much of the gas which has fallen from the edge of the circumbinary disk toward the binary is actually rejected, and it goes back to the circumbinary disk. That gas experiences what we would call a three-body interaction. So it's like doing the thing that happens in a reduced three-body problem. It's extracting angular momentum from the binary. So if all you do is throw gas near to the binary and allow that gas to be rejected back to the circumbinary disk, the binary will experience a rapid rate of orbital decay. Okay, because it's giving all its angular momentum to that gas which is rejected. And in contrast, if you throw gas toward the binary and you allow none of it to be rejected, the binary will be rapidly contracted. Okay, so it turns out that the tendency for binary to be either widened or contracted by its surrounding gas disk is coupled completely to the ratio, or I should say the efficiency at which gas is captured from the circumbinary disk onto the black holes. Okay, if that capture is inefficient, the tendency is to contract the binary. And if it's efficient, the gas is efficiently captured onto the black holes, the tendency is to then widen the binary. Okay.
Do you know how that or what scale to that happened, the angular momentum change happened with respect to, say, gravitational wave? Like, is there one more dominant than the other, or are they roughly the same?
So this is a great question. Okay, so it has to do with whether gas-driven orbital evolution dominates or gravitational wave orbital evolution dominates. And as I alluded to earlier, gravitational wave radiation, it only can cause contraction. So there is always a regime, and it is a realistic one, in which the binary is separated enough that its gravitational wave radiation is weak and the gas driving dominates. Okay, and there's a characteristic separation. It actually happens to be when the binary is within roughly a saltpeter time, 40 million years or so, of a gravitational wave driven merger. At that time scale onwards, the orbital evolution becomes dominated by the gravitational waves, and the gas becomes a subdominant effect in the orbital evolution. So we have this transition from gas dominated to gravitational wave dominated orbital evolution. Yeah, it's a good one. Yeah. Okay, this is another piece of basic physics that I like to share a lot. Essentially, when you put a disk around a central object, the central object has a finite lever arm, right? A binary surely has a big, relatively large lever arm, right? Separated by hundredths of a parsec or something. That means that it is, just by very nature of there being an angular momentum exchange between the gas and the binary. The accretion disk around the binary has to be conducting angular momentum. We call that a J dot, or an angular momentum flux, but the disk has to be carrying angular momentum either inwards or outwards, depending on, right, its effect on the binary. So if the binary is being contracted by the disk, it means the angular momentum needs to be flowing outwards through the disk. We have an outward angular momentum current. Accretion disks reflect their angular momentum current in how they distribute mass radially. Okay, so disks that are bringing angular momentum inwards toward their central object, they're deficient in mass at small radii. Their mass density radial profiles go down as you get closer to the central object. And disks that conduct angular momentum outwards do the opposite. They have a surplus of mass near the inner edge of the disk. So the accretion disk radial structure reflects this torque coupling with the binary. Now, as the binary contracts, its lever arm is decreasing, and that corresponds also to a decrease in the strength of the torque coupling. Okay, so that means that the disk is trying to respond by evolving away from its modified mass distribution to account for the angular momentum current toward a zero angular momentum mass distribution. Okay, that evolution means that mass is either being delivered to the binary at a relatively increased or relatively decreased rate, corresponding to the sign of this torque coupling. Okay. So what that means is that in a binary that's undergoing a gravitational wave-driven in-spiral, we can actually expect there to be a trend in the rate at which mass is being delivered onto the black holes. Okay, that trend would manifest over months up to decades. Okay, and what we found, my group at Clemson, is that this trend is actually computable from a very simple model. And so this is I don't have time to go into this in detail, but we essentially calculated new exact solutions to this equation of motion for an accretion disk. Okay, it's based on this picture here in which the binary is experiencing is contracting and therefore producing a torque on the disk that weakens over time. Right? So we have a new time-dependent solution to this equation. And what it predicts are these two things: the rate of mass that's delivered to the binary as a function of time before the system merges, and the rate of mass delivered after it merges. So we developed this formalism analytically, and then we tested it numerically. Okay, and Sam Fian, who's here in the room, was very instrumental in producing this this comparison. But this is a three-way comparison showing really good accuracy of that model, predicting that this sort of weakening torque effect leads to a long-term trend in the accretion luminosity. All right, so I'll say just a couple things about this three-way comparison. There are two codes there and one analytic model. So there's a 2D code, the Sailfish code, where you saw a movie a few slides back. A 1D code, which numerically solves the 1D disk structure equation. And then the analytic model. Okay, and all three of them show extremely good agreement in terms of predicting the rate of mass that's delivered to the black holes both before and after, right? They also, at the same time, the model is predicting the time-dependent disk radial structure, right? And that corresponds to a quasi-thermal radiation spectrum that evolves over time, and then we can construct model light curves from that, and that's what's shown here. And what I did here is I showed one model light curve. I chose these energy bins kind of as motivated by UV soft X-ray and hard X-ray observatories. We see is that there is a brightening that happens around the time of the merger when the disk is exerting a negative torque on the binary, right? And there's a dimming trend around the time of the merger when the disk is exerting a positive torque on the binary, right? You might say, well, if the torque is positive, why is the binary contracting at all? Okay, we've stipulated there that it's in the gravitational wave-driven regime. So even though the gas is exerting a positive torque on the binary is decaying because of gravitational wave radiation. So what this is leading us to predict is that there ought to be, when binaries merge, two different kinds of characteristic evolution of the light curve. Okay, and those two different kinds, we call them type A and type B for attenuating and brightening. And essentially, these things ought to be changing look AGNs, which exist. Right? AGNs, in perhaps a dozen or so documented cases, exhibit sort of changes in their brightness and their colors over month to year like timescales. Okay, so what we have suggested is that perhaps some of these changing look AGN events, especially those for which there's no X-ray absorption, that means that that the change in luminosity must have been a result of an alteration in the accretion disk structure. Those things could have been binary mergers. All right. And what this also predicts is that in the era of LISA, when LISA will potentially be able to measure the environmental effect on the gravitational wave in spiral, there ought to be a correlation between the whether a binary is inspiraling faster or slower than the vacuum GR prediction, and whether the host galaxy exhibited a brightening or a dimming. And so we're predicting that there should be a correlation there, that AGNs that brighten around the time of a merger should show a dephasing effect in the slower direction. And yeah, that is slowed. Like the actual the gravitational wave signal should lag a little bit the vacuum GR prediction and vice versa. Okay, good. I'm just going to say very briefly that we're also looking into stochastic variability signatures. This is a computationally very challenging to do. So we need very high resolution simulations. The objective here is to measure the short timescale variability of the accretion rate onto both a primary and a secondary black hole. And so this is a system that has a 5-to-1 mass ratio. This smaller black hole is taking gas from the circumbinary disk, passing much of it to the primary black hole. And what we're doing here is we're measuring the power spectral distribution of the time series of the mass being delivered to each of those holes. Okay. The motivation for this is that if there is any kind of a characteristic signature in the stochastic variability of the mass delivery rate, that could enable us to identify binary black hole candidates without periodicity searches. All right, so that would potentially render systems that have very long periods, like inaccessible, over human lifetimes, to selection as binary candidates based on some kind of aspect of their stochastic variability. So this is work by my graduate student, Akhil Nair, who's a third-year student. And he found this universal power spectral distribution. It has a -3 index. We understand where this comes from now, and it's actually not too surprising in hindsight. It is essentially what you get if you wiggle a viscous disk from a fixed radius. But this -3 slope is a bit steeper than is characteristic for AGNs. Most AGNs show PSDs that are more like have -2 or even a little bit shallower than that. Okay, so this is work in progress, but we're hoping that the shape of the power spectral distribution here could potentially be used as a way to identify binary candidates based on their stochastic variability. Okay, thereby completely sidestepping the need to carry out periodicity. Well, I should say adding to periodicity searches. This would be a new way of identifying binary candidates.
What frequency observation is that?
So this is all, again, it's actually dimension free. Okay, but if these are 10⁷ solar mass black holes, which would be characteristic for LISA sources, then the 0 frequency here, or 10⁻⁻⁴ orbital frequency, that would correspond to. Sorry, did you mean light photon energy?
Yeah,
Okay, photon energy, UVs.
this is UV.
UVs, yeah, this would be, but what we're doing here is actually taking the PSD of the mass accretion rate. Okay, and that tracks pretty closely the UV light curve. Okay, yeah. So in terms of photon energies here, we're talking optical to UV. In terms of the temporal frequency, we're talking month-like. Okay, so I'm going to skip this result on eccentricity driving. It's an interesting dynamical result, but what I want to get to is this point about the AI. So all the simulations that I showed are based on really simplistic physics. Okay, that doing simple physics allows us to use a simple code. Sailfish is just 2,500 lines code. It's not too serious. But we actually need that simplicity in order to carry out really high fidelity physics simulations. We need to be able to repeat these simulations over many different parameters, evolve them for thousands or even tens of thousands of binary orbits. We need to be able to do them at different grid resolutions to ensure that we've got a numerically converged calculation. So the simplicity of the physics is really necessary, I think, in order for us to really have a high degree of confidence in the fidelity of the numerical calculation. But we can't say that we're really solving the binary black hole accretion problem unless we're also putting in all the other physics, which is immensely complicated. Okay, but just to, I mean, you would need to solve numerical relativity because you need a self-consistent time evolving metric. Okay, you need MHD, magnetohydrodynamics, because the magnetic fields are present in the plasma and they dictate the whole accretion system. And you need radiative transfer. So putting all these things together into a single code is just not, there are groups who are attempting it. Nobody has yet got the third ingredient yet, but I expect that to come very soon. Okay, but those groups are not able to do simulations with very, very high numerical fidelity. Okay, they can get a picture of what's going on. Okay, but those codes are just incredibly complicated. I would call them like gruesome, sort of. It's insanely complicated. Much is learned from these simulations, right? But and we are going in this direction as well. But I would say that we're not in a state yet where we could say, okay, we have a well-posed, trustable code that implements all of these ingredients, okay, in a reproducible fashion. So what I want to bring to everybody's attention is the potential for AI to help make astrophysics simulation codes more reproducible. All right. And so, what we want from these codes is for them to solve well-posed systems. Okay, that is for the physics to be expressible analytically. We know precisely which physics ingredients are going in. The approximations are all well posed. We need these codes to be performant because the expense in terms of flops is very high. So we want to use all the CPU cores and all the GPUs on every node of a cluster if at all possible. And we want the science to be reproducible. Okay, so in an ideal world, what I think that would mean is that any science results derived from the code are published along with a full description of what the code does. Okay, loosely speaking, a code paper. But that is not really how things work in practice. We have these frameworks that float around. Everybody has their own variation of those frameworks. And science results are not published alongside every single modification to a framework that was used to arrive at a science result. So what I'm playing around with now is the idea of writing specifications for code, so specs for short. The spec is illustrated here. It's a human readable plain text description. It's essentially a code paper, right? But it's in a form that's easily, it's kind of minimal. Okay, a code paper has tests and it has text and discussion. The spec is just the bare minimum amount of text to uniquely explain what the code does. And the neat thing is that an AI can interpret this thing really well. And then the AI can actually implement that in any language you ask it to. So I asked it to write a web app out of this. This is the spec for Sailfish, by the way. So these are all the equations that are solved in the simulation movies that you saw. So I asked the AI to write a code based on this spec, and it rewrote Sailfish. Okay. I asked it to, I should say what I'm using. I don't mean to be advertising for Claude Code, but I did find it was outperforming the other AIs at this time. I also wanted to illustrate what I mean by coding agent. So this is an AI programming agent. It's not a chatbot, or you could say it is a chatbot, but it's like doing more than a chatbot does. Okay, it's iterating. It's doing complete write, test, debug cycles. And this is a movie of my computer doing that. So you can feed the spec into the AI and you can say, hey, implement this code in whatever language. You can say, do it in JavaScript, say, do it in C, do it on GPUs. Now, in practice, that has turned out to actually, it doesn't yield the most readable code. Okay, so in my own experience, what I found is that if you ask it to generate a monolithic C code, it's not something you really want to maintain any more than you want to maintain any of these massive simulation frameworks. Okay, so on the other hand, I found that if you give it a very clean set of abstractions to write the code on, it does write absolutely beautiful code. Okay, and those abstractions you can also engineer collaboratively with the AI. Okay, so what from my limited experience at this stage, What seems to be the best idea to me is to engineer reusable abstractions, essentially to abstract away the execution environment, GPU, CPU, parallelism, stuff like that. Make sure the AI knows how to utilize those abstractions. It does seem to be very good at doing that. And then feed it a spec, which is physics specific and hardware agnostic. And you ask the AI to implement the physics based on those programming abstractions. That seems like it is working really well. Okay. And I think it does have the potential to make these codes much more maintainable and more reproducible. Okay. When you submit a paper, essentially, you could send in your spec as well. That would be published along with the science results. Okay, and that spec would uniquely explain what numerical calculation was carried out to get the science. So I see I've gone the whole 60 minutes, but I hope there's still time for a couple of questions. I'm here the rest of the afternoon, so I'm glad to have more discussions. So thank you.
And I think we do have time for a few quick questions.
Do you, out of curiosity, benchmark the AI's version with yours?
Yeah, it's just as good. That's because I mean I'm not writing in assembly, you know. I'm writing, you know, reasonably straightforward C code, and the AI does the same thing. Okay, so with compiler optimizations on, it's going to emit a code which is performing at a very similar level to handwritten C code. Yeah.
Yeah. So you must have heard this question a million times, but I would like to know your answer. So you do all of your simulations, the beautiful pictures in 2D,
Yeah.
right? So is going to, I mean, 3D, of course, is much more expensive, etc., etc. But your take, do you expect that to be just a minor modification, which is still the same answers, or are you expecting big changes?
Here's the okay, yeah. Of course, I get this question all the time.
Every time.
And so I think there is a limit in which this could be accurate. Relatively cold disks, thin and cold disks, negligible mass loss in the vertical direction. One thing I think is robust though is I mean, assuming the mass flows conservative, then you're basically just solving here equations of angular momentum and mass conservation. Okay, and since I think those two conservation laws dictate broadly the behavior of the overall accretion system. So I think from that point of view, that you're essentially just tracking the flow of conserved quantities, the 2D approximation is giving you a non-misleading first approximation. So I do think all bets are probably off if the disk has gotten thick, right?
I guess part of my question is, what are real systems like on these scales?
Yeah, and
Are they like your thin models, or
I'm dying to know.
do they have mass loss?
No, I'm dying to know. I mean, surely they have winds, obviously, right? And angular momentum and mass are both lost through those winds. But we don't know. And I mean, you know, are AGN disks like thin at large distances and thicker close to the center? Probably, right? We don't know how extended they are either, right? Like, so a circumbinary accretion disk, we don't really know how many how many binary separations the disk extends, right? X-ray reverberation mappings say that accretion disks extend to, what is it, tens or 100 light days or so. But that is not very far, actually. I mean, that's comparable to the binary orbit. So there are so many questions that I have for people who study AGNs and about what they believe the disk structures to really be like, because, you know, for all I know, this could be absolute fiction, you know, as far as maybe disks don't really look like this around binaries. So I feel like that is the question. So yeah, any way to get empirical constraints on the actual structure and appearance, AGN disks highly valuable. Yeah.
So I think we are a few minutes beyond the hour. So if anyone has like an urgent question,
Let me take one more.
The Zoom question with you. Like the Zoom.
yeah, especially if it's a quick one.
Fabiola asks, when you explain the intrinsic variability we expect to observe in these systems,
why there are only very unequal mass systems in the pictures you have showed.
Okay, yeah, that's a good question. This was actually for convenience. Okay, there's absolutely good reason to have started with an equal mass system for the purpose of examining the stochastic variability of the accretion. There would have been every good reason to do that. Actually, the reason we did this is because we have specialized grid, which is polar and has the hole centered on the primary. So the hole wobbles with the primary. Okay, if we choose a mass ratio that is too high, then that hole will wobble too much and it produces some systematic errors that we don't like. So out of numerical convenience, we decided to study 5:1 mass ratio system. It does actually make the problem a little bit richer because each of the two components, those have distinct power spectral distributions. Okay, and they also emit at distinct photon energies. Right, so it makes the problem a little bit richer in addition to being convenient. But if we were following a most systematic approach, we would start with an equal mass system. So, okay, so
Yeah, so Jonathan will be here with us, and there are still slots to sign up for meetings with him. Otherwise, we can chat and ask and answer remaining questions at lunch. And yeah, with that we can close the BHI Colloquium for today.